As we have discussed in the last class, that we have different types of power voltages. Mainly, we classified as temporary over voltage, switching over voltage, and lightning over voltage. In the class of temporary over voltage, the most dominating one is single line to ground fault. We basically most dominating is unsymmetrical fault, and we have seen that even within the unsymmetrical fault, the most dominating is single line to ground fault. So whatever is the over voltage dictated by single line to ground fault, that will be the our worst condition over voltage for temporary over voltage. Then we also discussed that in case of single line to ground fault, the healthy phase voltage, that is, if we say that fault is in phase A, then the healthy phase means B and C, or if the single line to ground fault occurs on phase B, then the healthy phases are A and C. We have derived this expression that in simplest form, the healthy phase voltage magnitude, and fortunately, though in phase the voltage B and C will be slightly different, but in magnitude, both healthy phase voltages in case of single line to ground fault is the same, is same value, and it depends on mainly, as you can see in this expression, this is the phase value itself. So this is the phase voltage. This is the voltage. In fact, phase normal phase voltage, normal phase voltage. This is in fact the voltage just before the fault occurs. That is called also called pre-fault voltage. Pre-fault voltage. That is when the system was in normal condition. So this is the and the rest everything is just the ratio of x naught by x1. Here x1 is the normally the reactance or impedance we call in normal. Whenever we don't say any sequence impedance, that you must remember that whatever we are modeling in normal condition in the steady state, that is itself is the positive sequence impedance. So whenever we analyze a line, I say that it has the impedance of Z, which if I do not spell anything means that is positive sequence impedance. And this x naught, also known as zero sequence, is basically the combination of the positive sequence as well as the neutral condition. So this zero sequence impedance of any electrical device is dictated by its neutral grounding. So that means when we say that x naught is higher, means neutral impedance is also higher. If I say x naught is lower, because x naught in general is represented by x naught is equal to, you might remember, is equal to x1 plus 3 times of neutral impedance. So if as in case of isolated neutral, this becomes infinity, and that's why the overall x naught, that, and that's why people also call that if we model the system with isolated neutral, then zero sequence equivalent circuit diagram is open circuited. So we also discussed that for solidly grounded system, this x naught by x1, as I have just mentioned you, that since x naught is equal to x1 plus 3xn, solidly grounded means that is neutral impedance is 0. So in that case, this simply the x naught equal to x1, and that's why it is 1. So if we put, just very simply put in the above equation, no worry, no dot at all, no confusion at all, that if we put the x naught upon x1 is equal to 1 in this equation, this quantity is 1, this quantity is 1, and this itself is 1, and this also 1. So as you can see that 1 plus 1 plus 1 root 3, multiply it by root 3, it becomes 3, and here 1 plus 2 is 3. So that means 3 by 3. So it's only, in case of that, it will be only the phase voltage. So it is only the phase voltage. And we say that in case of solidly grounded system, that's why the conclusion is, in case of solidly grounded system, in case of single line to ground fault, there is with solidly grounded system there is no over voltage at all. When we say that phase volt is same as the phase voltage means there is no over voltage. For isolated neutral system, this x naught by x1 tends to infinity, and if it tends to infinity, just you know the limiting value or to compute. If you do this limiting value, you will soon find that this quantity, this quantity becomes one. This quantity becomes one once x naught by x1 tends to infinity. So that's why in that case, the voltage magnitude of the healthy phase, either B or C, is can be expressed as root 3 times of EA, which is line voltage. So since BB is represented in line voltage, if we also like to, in case of, sorry, isolated neutral, this is line voltage. The same thing we can also express for the solidly grounded system, only because we know the correlation between the line voltage and phase voltage is 1 by root 3 times less than the line voltage. So therefore, now only simplicity to understand is both are expressed in terms of line voltage. So we can, in general, we can say that healthy phase voltage in case of single line to ground fault is very now our conclusion is can be expressed as k times line voltage, where this k, of course, you know, I have mentioned you the last time also that this K must lie in, because these are the two extreme conditions. Where from where this we are moving the isolated neutral from the sorry, isolated neutral, one extreme condition, and another is solidly grounded system. All the other neutral conditions will be in between these two. So these two are the two extreme conditions. So this K will vary from 1 by root 3 to 1. And also we discussed that higher is the value of K, this K, that means if this K is towards this direction, the insulation level will be high, because once the K will be higher, this K will be higher, the over voltage will be higher, and lower will be the K, lower will be. But this K lower we cannot achieve just without the investment. So to make this K lower, we have to invest more on earthing costs. So always there is a compromise where to invest more on the earthing or to invest more on the insulation. We need to make the compromise, and that compromise is known as effective grounded system. So that compromise, in fact, is the effective grounding system. The definition of the effective grounded system is a compromised practical grounding. So because whatever example the two extreme condition I have given you in previous slide is the ideal one. So in practical case, we have the compromised practical grounding system where the K will be in between that, and a proper definition for effective grounding system. That's why can be said as a system or a portion of system can be said to be effectively grounded when, in the event of single line to ground fault, the over voltage in healthy phase does not exceed a fixed percent. What is the fixed percent? Fixed percentage means fixing the value of K. It's nothing different. The fixed percentage means just fix the value of K. And as you know that if you put the lower value of K, you need more earthing costs, higher, and so I have just explained it. So different utilities has a varying definition of effective grounded system. What does it mean by varying definition? Means they say that is if their best effective grounding system, but they put the value of this K different. Some people may take K equal to 1 itself. That's the effective grounding for them. Mainly in Europe, sorry, in New Zealand, or also observed in some of the African countries. Many African countries, they use isolated neutral system because their soil resistivity is quite high, and reducing the earthing impedance is very costly affairs. So in India, in fact, we follow all the standards and others without hesitation to say that Indian, and they use for this the definition for the effective grounding system, the value of K Indian use as zero point 0.8, and that's why we in so many books written by Indian they have made the definition of the effective grounding system universally, as for which the healthy phase voltage in case of single line to ground fault is 80% of the line to line voltage. But I like to confirm you that is the effective grounding is more general, will be better. It also to be noted that once we will proceed, we will see become more clear about this line, that it might be necessary that in some cases, depending upon the voltage level. So, for example, for one voltage level, we may choose zero point 0.8. For another voltage, maybe better or optimum option could be to use the zero point 0.9 or so on. So just now, if I take an example, say I want to give you an example to calculate now the temporary over voltage in general, temporary over voltage for say, yes, already written. The problem is already written. So compute the temporary over voltage for a 132 kV transmission line for isolated neutral system and effective grounded system. I think that it's not difficult now for you to calculate this. Very simple. Just use calculate you together with me. So first of all, what you have to do is you need to calculate the maximum system voltage, since this is 132 kV system. Therefore, so first of all, just calculate the maximum system voltage, and that is 132. Since it is 132 kV, so multiplying factor will be 1.1, and then this is your maximum system voltage. For isolated neutral system, this itself is the temporary hour voltage. Whereas for effective grounded system, just multiply this quantity by 0.8, you will get the temporary hour voltage. So it's very simple. Now I have already calculated for you for the in case of different standard voltage from 11, which we use 33, 66, 132, 220, 400, and 765, the as the maximum system voltage, as you can see, that beyond this we use just the 1.05 multiplier, and for effective grounded system and for isolated grounded system. So this is almost the universal. So if this quantity may change, this column may change if our definition for the effectively grounded system will change. Right now, this has been calculated for the value of K equals to 0.8, but other this quantity remains same always. So this tables gives you just an idea that what could be the voltage level in case of single line to ground fault. Now, with this brief discussion overview of temporary hour voltage, now let's shift to some idea about the lightning hour voltage. So now, on since the beginning of this class, I have several times now given you the idea that the main purpose of the earth wire in a overhead transmission line is to shield the transmission line from the lightning strokes. And in fact, it's a very effective. So it has been experienced practically that if the line is properly means effectively, the shielding wire is placed effectively. How to place, little bit idea I have given you 2 3 class before, that when we may need single earth wire, when we need the double earth wire, the shielding angle should be as small as possible. So rarely if we make that, then rarely a conductor if experience direct lightning. What does it mean? That means once the lightning strike comes, it occurs on the earth wire rather than the conductor. So strike, so that lightning strike. So lightning strikes either on the earth wire or on the tower itself. So if you take that, how often the lightning directly strikes on the conductor, it's even less than a single percent, 1%. And why it is also including that the tower itself is because the tower is directly connected to the earth wire itself. So if you have, say, for example, a line, then whether you say that, like, if the lightning strikes at this point, if the lightning strikes at this point, means we are saying that it is at the earth wire. What about if the lightning strikes at this point? If the lightning strikes, this is in fact in the earth wire as well as in the tower itself. But again, the chances, the probability will be smaller because this is a very a small span relative to the long span of the. So if the lightning strikes here, what is happening? Let's consider. So assuming that lightning is striking, is striking on the middle of this span. So as you know that what lightning is in fact a flow of heavy current. So say this is the lightning current. Lightning current, I lightning is. I'm not going to discuss with you the mechanism of lightning because it will take, maybe taking more than 1 or 2 periods. Just for that purpose, I expect that fundamental things about the lightning you understand. So if lightning strikes at this point, then, as for any electrical circuit, it may try to travel in either direction, either in this direction, or because the electrical path at this point is only two. So it will move along this direction or in this direction. You know that you might be have studied the traveling wave, that or high frequency wave, when travel in through a conductor, then the impedance offered by that, for that wave, is not the line impedance but the surge, called the surge impedance or characteristic impedance. So that means the impedance offered by this lightning current when it moves either in this direction or this direction, the impedance offered will be the characteristic impedance of the earth wire. I have mentioned you that for a power conductor, this characteristic impedance or surge impedance is around 400 ohm. The earth wire, it's slightly greater than that because the size of this earth wire is always much lesser in comparison to the power conductor. So this GMR is smaller, means inductance is higher. So earth wire has this characteristic impedance in the range of 500 ohm. It's no matter whether we say 400 or 500 for purpose what we are going to discuss, but yes, this is the practical value, that is, it is around 500 ohm. So now what will happen when this lightning currents? So of course at this point the path impedance for both the way, whether it move in this or this, is the same. Therefore half of this lightning current will move in this direction and half of this lightning current will try to move in this direction. Now after some times this, it will reach to this point. Now it has two paths. I have mentioned you very clearly that this earth wire is directly connected to this tower structure, no insulator. So that means once the current is coming to this point, now this current has again the two paths. One option is to go in this direction and another is to pass through the tower itself. Now the tower resistance in fact is high but relatively much smaller than this. So if you consider for any tower, it is around 50 to 60 ohm, 50 to 70 ohm. So tower resistance. This, in fact, this is not the tower resistance, because the tower is a metallic structure. It has the resistance of very, very small. Only the main resistance is the hair, that is the earthing resistance, because ultimately it has to pass through the earth. So the earth, this 550 to 70 ohm is mainly consisting by this earthing resistance. So naturally what you can see is, when the lightning current reaches to this point, most of the this current will try to flow through this path, because current always try to flow through the least impedance path, and only few small current will go. Once it will go, a small current will go here, the same thing will happen at this point, because now most of the current here and only a small portion here. So since this is almost 10 times, so 10 times of the, if the 10 current will go here, only one current will go in this direction, as you can see. And also, since the value of this lightning current is not fixed, so just we may consider mainly how much current will can flow through this tower to ground is more important. Now secondly, the lightning may strike, as have been seen here, directly on the tower point itself. Then what will happen? Again, it has a three paths, because the earth wire is connected to this. And as we have just discussed in this case, again, the maximum current will flow through this lightning, this tower. Only a small current will go in this way. This, from the current of magnitude of current which is passing through the tower, as you can now easily convince yourself that this situation be more severe than this. That is the second case, when the lightning directly strikes on the tower, the current flowing here could be expected to be higher, because at this point, if it is the mid span, only half of the current is reaching here, and even if that half whole is going here, then the current is smaller. But since the not always the lightning has the same current, so we have to consider the worst scenario. So what we can, why I have discussed all of these things with you is, in either case, whether the lightning strikes on the mid span or lightning strikes on the tower itself, the tower voltage, how much is the voltage at the tower? Because without this lightning current, you know that since this is uh, grounded, and no current is flowing through the tower. So before the lightning, the potential of the all tower structure, metallic structure, of course, is the zero potential. But in case of lightning current, the tower voltage is how much current is flowing through the tower, how much current is flowing through the tower, times the resistance of the tower. I have written RF. Why? Because as I have told you, the metallic structure of the tower offers very, very less resistance. So whenever we say that tower resistance is basically the tower footing resistance, it is called tower footing resistance. This one, tower footing resistance. So that is, this is the resistance between the earth and the tower. This whole structure may be 1 or 2 ohm, not more than that. So, but this tower footing resistance may be around 50, 60, or sometimes 80, or sometimes even 100 ohm. So this, that's why F subscript is there. So in either case, I have told you that, so mainly the what will be the voltage at the tower structure, and since the tower is a metallic structure, so whatever is the voltage of the tower will be this throughout this volt, at this point, all along the tower will almost be the same voltage. Now, what will be the voltage across the insulator in that case? So this is the insulator. Now you have calculated this is the voltage along the tower. So this is the tower voltage now. Tower voltage at this point. And you know that this conductor is at the system voltage. This is the system voltage. System voltage. Usually when you try to find out the voltage between any 2 points, then you know that usually what you do is that if this is say V1 and this is V2, then always the voltage across this you use as V1 minus V2. But here I have written plus. Why? Why plus? This is because the lightning, as you have seen that this is the voltage. So you have a, say, you have a V1, as I have mentioned here, V1 and V2. So say V1 is something fixed, right? And V2 is, as you know, that the voltage at this conductor is a sinusoidal variation. So sometimes it becomes positive and sometimes it becomes negative, right? Say V1 is always is a fixed value. So either positive or negative. So it will be fixed. And V2 varying sinusoidally. So what will be the worst case scenario of V1 minus V2? If we make at this instant of time, this will be the best. And worst will be when we, because lightning may occur at this instant of time or this instant of time. We do not know when the lightning will occur. It's not that we are always fortunate and lightning will occur only always at this point. Lightning may occur when the power conductor voltage at that instant of time is passing through the maximum negative. So if we say that this could be the worst condition, so under that condition you can see that the V1 minus V2 is this minus this means, and since this itself is, so this plus this, right? So that's why, or if you plot this in same scale, then you can understand bit more easily that this is your voltage and another is conductor voltages look like this. So this is the best condition voltage and this is the worst condition voltage. This is V1 and this value is B2 and this is B1 minus B2, which is nothing but, some people also call this lightning current as negative current, because what their logic is, that is, whenever the lightning comes around this, then how it strike is, that is because of the induction effect, the nearby earth object, so many electrons are already, positive charge is here already deposited here, and once it strikes the, this is the electron flow, the lightning is the electron flow which is the negative charge. So once it touches this point, and since that path is already ionized, so they think that their logic is that this current, this all this positive charge very rapidly move towards the cloud. So if we use that logic, then what you can see that the current always flows from high voltage to low voltage in the resistive circuit, because this is just a resistive circuit we are treating it. So the voltage at this point will be negative. But even you take this as negative voltage or positive voltage, now you have realized that we have to consider the worst condition. So no matter whether in mathematical, because if I write this as minus, if I write this is the minus, then say this, then this will be the, that would have been the worst condition. Again, I have to write in that case that this minus and this also took the minus, because now in that case we could have taken minus B1. So whether you say that lightning current is positive or negative, no matter, the main, we are interested in the magnitude of the voltage, how much this insulator, the voltage across this insulator will be under the lightning condition, and that is this. So I have tried to convince you two major points. One is this is correct, this plus is not wrong. And secondly, whether you say that the lightning current direction is positive or negative, the worst case voltage is the same. So as I have mentioned you that typical lightning current, typical lightning current. Now the lightning current, the if the you go through the literature, it convey the message that the lightning current may vary from a fraction of kiloampere to 20, 40 up to 40 kiloampere. But it has been said that the lightning current passing the magnitude of over 10 kilo ampere is the probability is very very low, because the light in lightning most of the things are the probabilistic theory, because it's not a certain mechanism, it's an uncertainty. So it has been seen that only about in 100, if lightning strikes say for 108 times, then only one times there is the probability that the lightning current will exceed this 10 kilo ampere value. So most of the analysis done so far, for the protection or for insulation design in case of from the lightning, they use the typical value of lightning current of 10 kilo ampere. But this does not mean that lightning current is always 10 kilo ampere. Rarely it may be greater than this, and often most value of the lightning current is lesser than this 10 kilo ampere. But so that's why even if the lightning current, we design all the system for say 10 kilo ampere and the lightning current comes the 40 kilo ampere, definitely our system will not be protected. So we cannot guarantee that our protection system is 100%, but we cannot go for that rare condition because the cost will increase. So with this, just try to find out what will be the say the voltage across the insulator if our system voltage is say 66 kV. What will be that? Now, worst case for the lightning, as you have seen that lightning may strikes on this value and in the tower itself. And secondly, the lightning current value is not fixed. So even if it is strikes in the mid span and we say that half is going this and half is going this, what is the half? Half of what? Well, for 28 kilo ampere, then 10 kilo ampere. For 10 ampere, then 5 kilo ampere. For 40, it may be 20 and 20. So since this is not known, and also the worst case could be that is the lightning current striking directly on the tower itself, therefore we may take consider that this 10 kilo ampere is passing through the tower itself, right? So that's why you first calculate the tower voltage. So tower voltage, that's why will be equal to, as it is already mentioned here in the formula, will be this 10 times 50. If we consider that tower footing resistance is 50 ohm, so this will be 500 kilo, because current is in kilo ampere, so it will be in kilo volt. But if we consider the 70, then this is 10 times 70, so 700 kilovolt. Now we need to compute for the what much is the voltage across the insulator. We need to compute this peak system voltage. What is the peak system voltage? For peak system voltage, you first need to calculate the maximum system voltage. So maximum system voltage, since our nominal voltage is 66 kV, so 66 times 1.1, 66 times 1.1. Now, system peak means, one thing I have not mentioned to you right now, that whenever we design we considering or we discussing about the insulation, then always think that we consider the insulation for phase peak. So it's not nothing to, because we have to often we have to insulate that voltage with respect to earth, and that's why we are considering for the single this phase voltage. So the first, then you need to calculate the phase voltage. So the phase voltage will be 66 times 1.1 divided by square root of 3. So this voltage is the RMS phase voltage. That's why, since this voltage is the RMS phase voltage, so the peak voltage is whatever is this times root 2. Now, one thing you might have been observed that I use the word maximum, and peak very consciously, because when you studied the very first year or something, you may call the, say, Vt you expressed as Vm sin omega t. Then you call Vm as maximum system voltage, maximum voltage. But now the definition for the maximum system voltage is something different. So in this course or now onwards, whenever I say maximum system voltage, means that is from this point of view. That is from the worst scenario of the operating voltage. Wherever that is the, when we define the maximum magnitude of a sinusoidal wave, we call it as peak voltage, right? So this is the calculation you can, how the steps how you can calculate. In fact, I have already calculated for you for the all the, because I have calculated this just using an Excel, and here we have all the possible nominal voltage we are talking about. Even you in Nepal, you might have heard that some 2 years back, the some ministers and others have started talking about 765 kV. So I have put it this value of the voltage also. Then for each of these, first step is to calculate the maximum system voltage, and then the peak voltage immediately, just as we have calculated in previous slide, that is just divide it by root 2. Sorry, this is the maximum system voltage. So yeah, divide it by root 3 and multiply it by root 2, you will get this. So the corresponding peak voltage. And as you have seen that the tower voltage, this tower voltage is only depends on how much is the lightning current. So this example has been taken that assuming that is 10 kilo ampere is passing through the tower, and based on their tower footing resistance. And one thing you might have observed, which I forget to mention you in the last class, that why the low tower resistance is risk requirement. Because if the tower resistance will be high, the voltage across the insulator in case of lightning becomes very high. So that's why when we discuss the air clearance calculation, that time, and also in the first class of the insulator design, I mentioned you that assume that the towers are very properly effectively grounded. So higher will be the tower footing resistance, more will be the tower voltage. So as you can see this. So definitely now, what will be the voltage across the insulator will be sum of this plus this. So this plus this. Or if you assume that tower resistance, footing resistance is 770 ohm, then in that case this plus this. So these two columns. That's why even for the voltage across the insulator, you can fill it that, yes, you, I have we have mentioned that there was in the very first class that going for higher voltage is always advantageous from conductor cost point of view, but we do not go because the insulation cost increases. And roughly we have considered that if we go for from V to 2V, the insulation cost will almost double. But if you look from here in this table, then you can see that for 11 kV you need, say, 709, and for 66 kV only this. So there is a marginal difference between these two. And if you going to design the insulation, one thing I would like to remind you again at this stage of time, that I have mentioned you that whenever we design the insulator, that insulator must be capable to withstand all continuous maximum system voltage, as well as the short time, all types of short time over voltages. So what does it mean? That if we have a, say, insulator, we have selected an insulator for any voltage level, then this should withstand how much is the maximum system voltage continuously, as well as this should withstand the whatever is the temporary voltage acting across it, lightning over voltage, acting across it, and the switching voltage acting along it. So all the three should, this insulator should be capable. So say this is the V1, this is V2, and this is V3. So that means this insulator should withstand all V1, V2, and V3. Now suppose say based on this V1, we have we may require how I will come later on, but say at this stage that for V1 it has say that okay, for that temporary voltage we require the 4 number of insulator, and say for switching we require 5 number of insulator, and if we say that for lightning we require 20 number of insulator. So this is the case usually seen at here. That's why I explained that this definitely is not a kind of optimum scenario, isn't it? Because what it says that just because of the lightning you require a very high number of insulator design. So usually in this case what is done is either this voltage has to be reduced, isn't it? Or you have to sacrifice just for the lightning so many cost for the insulator, though that number of insulator disk was not required for the temporary or switching or for the continuous. So that's why whenever we see this in our voltages of the different classes, we should think, we should look all these together. We cannot say it independently. So just to get that idea, in next table what I have done is I have compared whatever the temporary hour voltage we have calculated and the lightning voltage across the insulator we have just said calculated for all the system voltage, because this is just the two table I have shown you separately. So this is not a new calculation. This we have already calculated today itself. I have shown you that temporary hour voltage for ground effectively grounded system means for value of k equal to zero point 0.8, and isolated neutral system is looks like this, right? And lightning hour voltage. So now you can compare. That is, as for 11 kV, temporary hour voltage is maximum even in case of isolated neutral is 12.1 kV, whereas for even for the best case of the 50 ohm tower footing resistance, this is 509. Yeah, one good thing that is, of course, in this table you can see that throughout whatever is the voltage level, always the arrested lightning hour voltage is higher and higher. But one thing I had mentioned, also mentioned you in one of the class, that same insulator, same insulator can withstand can withstand more lightning voltage than temporary voltage. What does it mean? I have told you that any insulator, how much the voltage it can withstand without failure, not only depends upon the magnitude of the voltage, but also depends on how long that voltage will appear across the insulator. Since, and also we have discussed that lightning hour voltage appears for very small times in order of microsecond. So obviously the same insulator can withstand, say, if 10 kilovolt of 10 kilovolt of temporary hour voltage, then naturally the same insulator can withstand more lightning voltage. But this does not mean that more means infinity. Roughly, just if you see the insulation property and others through the experience, it has come that it's around 3 times. That means if an insulator can withstand of 10 kilovolt RMS, 10 kilovolt RMS, because this voltage, all these voltages are in RMS, you must remember. So what does it mean? That 3 times of RMS, because because temporary hour voltage can be expressed in terms of either in terms of RMS value or in terms of peak value. So sometimes people becomes confused. So that's why I mentioned you that roughly it is around 3 times. So if we go for even for that good thing, then now what I have done here is that for this much was already calculated. So I have calculated that if we use the insulator, say for the to protect the temporary over voltage of this much, then the same insulator without doing anything for what voltage it will can withstand for the lightning. Of course it is just the three times of this, so this is the three times of this. So throughout this I have done the three times. Looking to this table, I whether what you observe I don't know what's the, but I think I have observed both the good thing and some alarming situation. What is the good thing in this table? In good thing about in this table is, if you just look beyond 220 kilovolt insulator, 220 kilovolt, just look in this table, go beyond 220 means for 400, for 760 kV. If you just look this table, what you will find that the insulation level, because this is just the equivalent voltage, this is not the lightning voltage. So what does it mean? That if a insulation is designed at under this, if a insulator is designed to withstand the 420 kilovolt 420 kilovolt of temporary over voltage, it can withstand 1260 kilovolt of lightning voltage. And for 400 kilovolt, the lightning voltage itself is 1042.93 kilovolt. That means lesser than this. So we do not need any separate special provision for this voltage or this voltage. We don't need, because what does it mean? That once we insulate or our insulate, we design the insulator which can withstand at 400 kV. And very in simple language I tell you that what I mean to say is, if we design an insulator which can withstand their respective temporary over voltage for 400 kV, they automatically can withstand the probable lightning or voltage on that. So we do not have to go for any other special provision. So uh, beyond 220 kilovolt, the insulator designed to withstand temporary over voltage will automatically withstand lightning voltage, because the equivalent lightning withstand voltage for 400 kV is greater than the actual. This is the actual. This is the, again I repeat, this is very important point, because this is the actual lightning lightning or voltage at 400 kV system, isn't it? This is the actual, and this is the voltage a insulator can withstand if it can withstand the temporary over voltage on 400 kV. So what does it mean? That if we design an insulator which can withstand 420 kilovolt of temporary voltage, it has the capability to withstand the lightning over voltage up to this value. But in actual case, the lightning over voltage at 400 kV is most likely, is not guaranteed value. but most likely less than this. That's why it will automatically. But there is another alarming, that is the challenging part also. So as you can see, lower is the voltage. Now say just for 33 kV case. 33 kV case, the maximum temporary over voltage is 36.3 kV. So insulator which is capable to withstand only 36.3 kV can withstand only the 109 kilovolt of equivalent lightning over voltage. But in case of 33 kV, we have, so that means how many times? Almost 7 times, almost 7 times more insulator is required at 33 kV. At 33 kV, almost 7 times more level is required for to withstand just to because of lightning hour voltage. This will definitely is not the cost effective situation. So we must have some mechanism, especially for low voltage case. This may not required at high voltage case, but when the voltage level is very low, it is better that if possible try to reduce the, and just of course whenever we reduce the over voltage, then we need some extra cost, and that cost must be justify the voltage reduction rather than going for high insulation level. And one of the options used by the for the protection against lightning is the lightning arrestor. So what is a lightning arrestor? Just before going in detail with this, just understand what is the lightning arrestor. A lightning arrestor is just a non-linear resistor. Non-linear resistor. This is connected in between the power conductor. This is the power conductor. This is the power conductor. Power conductor, and the another terminal of this lightning arrestor is connected to the earth. This is earth. So there is two terminals in, if you see any lightning arrestor, just two terminal, one terminal connect to the power conductor, another to the earth. So it's a device used to divert the lightning strokes before it damages to the insulation, because even this lightning hour voltage will appear, it will take, if it will persist for some time along the insulation, then it can damage. But the idea is, if we can divert that hour voltage, one very universal statement is lightning cannot be avoided, it can only be diverted to the least impedance path. This is general, not even for the lightning arrestor in general. So the idea is that offer the lower resistance whenever lightning strikes on this line, so that it can divert it to the earth. So what is the basic feature of this lighting arrestor is, during normal voltage condition, that means this voltage, when this the voltage around it is say power frequency normal voltage, this is behaving like a open circuit. So the resistance offered by this lightning arrestor under this condition, the lightning arrestor resistance under this condition is infinity. So once it is infinity means this is open circuited. Whenever during the over voltage, when the voltage at this point exceeds a fixed preset value, when exceed it's called the spark over voltage. That voltage, preset voltage, is known as spark over voltage. It is conducting and acts as a closed circuit. So once it is a closed circuit, then current starts flowing through this. During conduction, what is required is, now once the current starts flowing through this, then definitely during even under condition of our voltage will be how much is the current flowing through this lightning arrestor times the resistance offered by this lightning arrestor. So the lightning arrestor resistance small must be small, otherwise this itself create the high voltage. and therefore the resistance of the lightning arrestor should be a non-linear, consist of a non-linear resistor. Non-linear resistor. This must be a nonlinear resistor. So the behavior of the nonlinear resistor, what it usually is, that is, as the current increases through it, its resistance should go on decreasing and decreasing. I will come this just now. So another important point is, since this lightning strikes comes for only for microsecond, and after some few microsecond it vanishes automatically. So one very important is, it might be one thing, you know, that you have an insulator, it across this insulator a high voltage, very high voltage appeared. Because of that it starts conducting. Now that voltage has disappeared, but you must remember that this path is already conducting ionized. So it will even now the voltage after the lighting disappeared, the voltage along this line is normal voltage, and the, there is a normal voltage and the path is already ionized. Therefore, even the lightning disappears, the current may flow through this. Only in two cases this current can stop flowing. One is disconnect this line from the source, so that there will be no flow of current, no voltage here, and no current flowing through this. Secondly is build the insulation itself within the lightning arrestor, so that once the light high frequency over voltage disappears, then insulation at under this condition should be built up automatically. In fact, in lightning arrestor, both is happening. In a very simple lightning arrestor, which use a simple lightning arrestor, is just a gap, air gap, nothing else. So just a air gap is also behaving like a lightning arrestor, usually in very low voltage system. So once a voltage across it exceeds a value, preset value, then air gap, this air gap ionized the conduction, the air breaks and the current starts flowing through this, and so it's diverted. Now once the lightning has gone, then what is still this current is going through it, and it behaves for a source end, it behaves like a short circuit. Now once the lightning has gone and the current continue to flow through it, because the normal system voltage is here. So now the relay at this point looks that this is not just a lightning, but it is a short circuit, and this they disconnect this. And once this disconnect, the ionized path vanishes, and after certain times, once then again if it is connected, then the air has already built up its, only it requires that one the chain of ionization should be break. And that's why this is also called sometimes as the temporary fault, line to ground fault. But in case of advanced lightning arrestor, what is that is, they have the ability to sense. They have, in advanced lightning arrestor, they have the ability to sense that the whatever is the current flowing through this lightning arrestor, is the is this current, whatever is the current flowing through this lightning arrestor, they can distinguish that whether this current is, whether this current is the high frequency current, high frequency current, or uh, power frequency current, power frequency current. So if once they, because definitely when this spark over, this high frequency current will flow, but after sometimes when the lightning disappears, once the lightning disappears, this current starts flowing through it. Once lightning disappears, then this power frequency current starts flowing through it. and then they understand that yes, lightning has already gone, so they build. Once this lightning or voltage disappears, it builds the dielectric property automatically. What does it mean? That means that this lightning arrestor is not expected to operate for even for the temporary over voltage, because if it's expected to operate for the temporary over voltage as well, then it cannot distinguish that whether, and it cannot rebuild its dielectric property in case of power frequency. So this lightning arrestor is designed to operate only for transient over voltage. No, it should not protect. This lightning arrestor is not designed to protect this line from temporary over voltage, because the all the over voltage in the line, as you might know, is not always only the transient over voltage. The over voltage may be the power frequency over voltage as well, but this lightning arrestor should discard the temporary over voltage. Don't care. They should not care about the whatever is the temporary over voltage, right? So lightning arrestor is only designed to operate for the lightning. So what does it mean? That it must withstand all possible temporary over voltage without a spark over, and that's why the lightning arrestor should withstand temporary over voltage. It should not spark over for, and that's why the voltage rating voltage rating of the lightning arrestor itself is defined as the temporary over voltage. So, for example, if we have a 11 kV system, what will be the rating of the lightning arrestor? Now you can say very easily. Sorry, what it is. Just now, I want to go back here. Say for 11 kV system, what should be the rating? Just nameplate rating of the lightning arrestor. It could be in between these two, isn't it? Because either for the effectively grounded system or isolated grounded. So some country where they prefer to have an isolated neutral system, then the lightning arrestor rating for them at 11 kV is around 12 kV. But for our country, in Nepal, we use the 10 kilovolt lightning arrestor at 11 kV, 30 kilovolt at 33 kV, and so on. So, what does it mean that what's the rating of the lightning arrestor? What's the rating of the lightning arrestor mean is the rating of the lightning arrestor means that it must withstand that power frequency over voltage without any sparking or without any conduction. Then there is a one definitely, therefore the spark over voltage of this lightning arrestor must be greater than this voltage. If it will be, the spark over voltage will be lesser than this, then definitely that lightning arrestor will conduct even in case of temporary over voltage. So that's why the spark over voltage of the lightning arrestor is always greater than the rated lightning arrestor voltage, and usually it is chosen around 1.5 times. Now, what will be happen if we go for below this? Say if we choose 1.2 instead of 1.5, then advantage is with this is the insulation level of whole system could have been reduced, because once it conduct at lower voltage itself, then it can protect from the any voltage over that. But if the disadvantage with this is, if we choose this ratio lower, then in some cases there may be probability that this lightning arrestor may conduct for the temporary over voltage itself. So therefore, with all safety margin and economy, many utility prefer to have the spark over voltage of around 1.5. But this does not mean that 1.4 is not taken. Some utility also take it as 1.4 or something like that. Okay. So now, what we have discussed so far, what is expected that whenever we put a lightning arrestor, then any equipment for which this lightning arrestor is designed. Now, the one thing when I'm saying that any equipment protected by lightning arrestor, now you must remember this now that the lightning arrestor is not just put to protect the overhead line insulator. It is, in fact, protect. It is the aim is to protect all the insulations of all the devices connected to the line. And in overhead line, you might know now that it is connected to along the line itself, the transformer and the line itself, because so many times the line has to be a step up and or a step down along the way from source to consumer end. So it's also designed to protect the transformer insulation as well as the line insulator. So that's why I'm writing here the any equipment protected by the lightning insulation means mainly basically here I mean is two transformer insulation and overhead line insulator need to withstand just over a voltage across terminal of the lightning arrestor while lightning arrestor is conducting. What does it mean? That once you have a lightning arrestor, so while it conducts, while it conducts, whatever is the voltage across is is of course the what is the I flowing through it times the resistance offered by this lightning arrestor. So all the equipment must be insulation level must be designed that, so that is if we say that insulation level of the equipment, then this V insulation of the equipment must be greater than this V, because this is the volt even this conduct, this is the voltage at this point. So once we protect this insulator for this transformer, then definitely it should withstand this voltage. Otherwise, if the insulator fails even lower than this, then there is no use of lightning arrestor. And so ideally, the lightning arrestor is expected to have a characteristic such that while conducting, the voltage across terminal is fixed. That means here I should mention that irrespective of the lightning arrestor current. What does it mean? That once it starts conducting, it should be fixed. It should fix the voltage, whatever is maybe the current flowing through it. Once so, it's if we consider the ideal volt time characteristic of any lightning arrestor, then it should be look like this. It should be look like this. So whatever may be the current flowing through it, its voltage should, what does it mean? Mathematically, it have the characteristic of voltage is equal to K times I zero. So once you have anything power zero, then you can expect that it is possible. I to the power 0 means now even 50 to power 0 is 1 and 1 power 0 is 1. So it will always fix to this value irrespective of the current. But practically, we cannot find any such material which has this linear characteristic. So practically, what is done is practically the volt time characteristic of lightning arrestor is set this V is equal to K times of K times of IN, where you must remember that if I put this N is equal to 1, what will happen? If N is equal to 1, this is the linear resistance. This K is the linear resistance. So if N is equal to 1 in this expression, it is the linear resistance, we call it. Linear resistance. Right? If N is equal to 0, then what was the desired? That was the ideal ideal characteristic. Ideal characteristic required. So what we can say is, what we required is that we cannot go for this, and once n the value of n is 1, then it is a linear. Therefore, as far as possible, the value of this n should be as close as possible to this 0. Therefore, and it depends of course with the material property. So n, the n in this expression depends on the material used in lightning arrestor. Basically, there are two types of material used in advanced lightning arresters. One is called silicon carbide. Here you can see in this graph silicon carbide, and another is called zinc oxide, which is also known as metal oxide. So zinc oxide has the value of this n as the property that we can even make this n even more closer to the 0 with respect to silicon carbide, and therefore for very good quality lightning arrestor is thought, which is a metal oxide insulator. So here in this graph you can see that the ideal characteristic, this is the ideal characteristic. This is the linear if without any, just put a resistance, and but basically it has the silicon carbide, slightly more voltage if the current passing through it is higher. It's saturated but slightly higher, right? And here it has bit better in zinc oxide. It saturates even for very small current. So the actual voltage across terminals of the lightning arrestor, when lightning, there is a definition. This I, just right now I have just mentioning you the voltage across lightning arrestor, voltage across lightning arrestor. This voltage I have many times I have used this, but now onwards we will use this voltage as a term called residual voltage. So what is the residual voltage? Residual voltage of a lightning arrestor is the voltage across the lightning arrestor when it conducts. Ideally, this ideally, 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 this residual voltage is fixed, fixed, irrespective of the current flowing through this. So this is the ideal characteristic. How much this fixed value is? The equivalent voltage for spark over voltage. Why I'm saying equivalent is the spark over voltage we have just defined is in terms of power frequency. So naturally, an insulator will spark over at higher voltage with high frequency. So that's why just the equivalence. But practically, these voltages may slightly increase as you can see with the current. So this the voltage ideally should across the lightning arrestor during conduction should be independent of the current through it, but slightly it depends on how much current flow through the lightning arrestor, and that current. So that means if the current flow through the lightning arrestor is higher, practically the residual voltage will be little bit higher, and in that case the insulation level of the insulator will also go to the higher side. So just understand that what are the factors, or summarize that what are the factors affecting this residual voltage. So that as we have just pointed out, higher will be the residual voltage of the lightning arrestor, higher will be the insulation level of the equipment, obviously, because the equipment insulation should withstand more voltage than whatever is the voltage across the lightning arrestor under the conduction. So this voltage, as we have just pointed out, depends on the spark over voltage itself. So this spark over voltage could be higher or lower in two ways. One way is, of course, for depending upon the one is depending upon the rating of the device this rating of the device. So of course the lower rating equipment will have lower spark over, and because we can say that for 33 kV and for 400 kV it will not be the same. So that's the one point. Second point, as you have seen, that this spark over voltage is also dependent on the temporary over voltage. This is important. So even for a given system voltage, if this temporary over voltage is higher, this spark over voltage is higher, isn't it? So in one way we can also say that the aim of the lightning arrestor, aim of the lightning arrestor is converting the lightning over voltage protection level to the temporary over voltage. That is the aim. But whether we achieve it or not depends on these two factors. One is material characteristics, as you have seen, that there are materials which can be a nonlinear resistance, but higher will be the current, the voltage is exceeding. So our aim was this much voltage, but with increase in the voltage, if the voltage passing through, sorry, if the current passing through the lightning resistor exceeds, then this voltage may go on this. That means this voltage, say under one particular lighting condition, the current through the lightning arrestor is this much, then voltage may be this. So this was equivalent to the spark over based on the temporary. But if this difference between these two is much higher, then the aim whatever is set here is a bit like less matched, right? So the current flowing through, how the current flowing through the lightning arrestor, how much current flows. So if we consider that this is the traveling wave along the line due to the lightning, this traveling wave when reaches to the lightning arrestor, then the bolt this current flowing through this depends upon the resistance of this and how much current. So just any, you know that if you have very difficulty in modeling, we do not know, because this is the nonlinear resistance, right? This is the nonlinear resistance. This the resistance of this lightning arrestor itself depends upon how much current flow through this. So that means we do not know, before before this starts conducting, we do not know what's the resistance of this lightning arrestor, but we have to guess that how much the current will may flow through this lightning arrestor. And that's how to model the circuit. You have studied in the first year itself, that if you say in first year what you have studied is, now suppose a very complex circuit, you have a very complex circuit, or in this circuit we know this, but we do not know this. This is not known. This is not known. And we want to find the how much will be the current flow through this. What do? You make first, the job is you make the Theveninized equivalent circuit looking from this port just, and the equivalent circuit will be VOC, or some people also call BTH, and then the RTH, and then this is the Thevenin's equivalent, and now we put this R here, because, and then we find how much is the current flow through this. So here also How we can Thevenize this circuit, how much current will flow through this is in think that this lightning arrestor is this is completely open circuit. So and the this transient voltage wave strikes at this point, and you might have studied somewhere in the traveling wave that when a traveling wave strikes uh, any point on this circuit which is open circuit, then it the reflection coefficient at this point is unity. That means whatever is the wave coming at this point, now it has reached at this point, the full wave is started reflecting going back to this point. So what does it mean? That if this point instead of the lightning arrestor, if it is open circuited, the voltage at this point would have been the twice of what is the voltage reaching at this point. So that's why that is in fact itself is the open circuit voltage. So this is 2 Vs. This is the Thevenin's equivalent voltage. Thevenin's equivalent voltage. What is the Thevenin's resistance then? Thevenin's resistance is the impedance offered by this path up to this point for this voltage, isn't it? And that is nothing but surge impedance, because a high frequency wave while travel along the line, the impedance offered by the line is not the real impedance of the line but is the surge impedance. So this is the Thevenin's equivalent impedance. Then your circuit equivalent circuit for the lightning arrestor will be, this is the lightning arrestor resistance, this is the resistance of the lightning resistor, this is the 2 times of the striking voltage, and this is the surge impedance line. Then what will be the expression for I from this expression? It will be the 2. Still we do not know what is the resistance at this point. So that's why this is put is, let's say this is VLA at this point. Then the current through this is whatever is the voltage here minus this voltage divided by this. So that's why this expression. But here we should understand that this VLA itself is a function of, so some iterative techniques is needed to solve this equation to find out what is the ILA, because this VLA itself is the function of ILA. I have just mentioned you that how it is related is this VLA is K times of ILA to the power N. This K and N can be obtained from the characteristic of the material used in the lightning arrestor. Sometimes the lightning arrestor manufacturer gives the voltage across it for 2-3 different lightning current, and if it we will get it for 2 current, then you can see that you can even can calculate, that is say for example for case 1 B is equal to 1, and for 2 again this is K and this is LA2 and this is N. So we have, if th- this and this is given and this and this is given, you can compute A and N, and that's why now for any given current you can find out this value. Here from this expression what I mean, see, I want to convey you is, what you can see here is this voltage definitely we expect lower for lower system voltage, isn't it? The lightning arrestor voltage, say for example, the voltage we expect here for 11 kV, 11 kV, what we expect is this voltage for 11 kV, for 11 kV, we expect is must be less than for 400 kV, isn't it? But these two quantity is not is independent of the system voltage, independent of the system voltage, because how much lightning current will flow, this is this Vs in fact is the multiple of the lightning current. This Vs is the multiple of the lightning current to the surge impedance, and it is beyond the control. So what you can see from these two factor, the two factor is lower is the system voltage, lower will be the system voltage, higher will be the lightning current, isn't it? Right? Higher will be the. So even this is a very alarming situation that even even with lightning arrestor, yes, if once we put the lightning arrestor, the voltage at this point will reduce. But even with lightning arrestor, the low voltage in low voltage system, in low voltage system, the practical residual voltage will be far from the ideal expectation with respect to with respect to with respect to high system voltage. Why? I have explained you. This is because in low system voltage, as you can see from this expression, lower will be the system voltage, higher is expectation of this difference. Higher is the this difference will be higher because this is fixed, independent of the voltage, and this we desire lower for lower voltage. So the lightning current will be, sorry, lightning arrest current through the lightning arrestor, in one word, current through the lightning arrestor expected higher for low system voltage than. So now even we put the lightning arrestor, this does not mean that it will take everything there on and we don't have to do any other things. It is expected that as far as possible, as far as possible, what should be done for this is this, if we could also make that, if we can make this a lower value, lower value, lower value with for for lower value for low system voltage, lower value for low system voltage, that's good, right? Right. Alternatively, what we can do is, if we can, second, this is the first thing we can do to reduce the lighting arrestor. This is to have lower current, lower current through lightning arrestor. This is the option. So how it can be done? This can be done is if we can reduce this Vs, and that is, as we in the very beginning of today's class we have discussed that the tower footing resistance also plays a role in case of the voltage due to the lightning. So if we reduce the tower footing, and when we need to reduce the more, give more focus to reduce the tower footing resistance in low voltage system. Lower is the system voltage we require, and this is usually not the practical risk, because you might have seen that in low voltage system we don't care much because it is a high power system, low power system as well. Another way could be to reduce this voltage difference. This voltage difference could be whatever may be the current, but limit the voltage just by controlling the material use. So means use very high quality material. That is also not used in low voltage system. So what is done is it is expected that in low voltage system, the residual voltage of the lightning arrestor is made little bit higher than. So what I mean is, say for example, if you have a 11 kV system and you have a 132 kV system, if you have a 11 kV system and 132 kV system, here we may expect that the residual voltage may be around 60 kV, and for this case this may be around 500 kV. So what I mean is, now you can see that this 60 kV of course is much lesser than something around 600 kV without lightning arrestor. But if you take the multiple of how many times, then here you can say that for six, this is around six times. But for this case, it is just around 313 and multiply by 4. So around less than 4 times, right? And if even if you go bigger, then this difference. So this difference is coming automatically. Just this is because of, if we do not do any further control, just put the lightning arrestor only. If we just put the lightning, because here in a small system voltage, the lightning arrestor current is higher. So that one more word term I would like to introduce you. This is called BIL. This is the full form of this is called basic insulation level. What is the basic insulation level? Is so before, just I would like to give you some background before defining this. So as we know that the lightning strikes only for few microseconds. During strike, it reaches to peak value very rapidly and decay relatively. This is well known fact, but the exact time vary from a fraction of microsecond to few microsecond. So it's very challenging to for a design engineer that what should be the time of operations should be taken for the lightning current or voltage. Hence, there is a standard practice to simulate the lightning wave by this wave. What does it mean? Is this is the this is your lightning. It reaches lightning wave simulation. This is just for simulation. This does not mean that all the lightning have the same characteristic. Practical, it varies. This is peak time. This is called also called front time, TF. That is time to reach the lightning strike from 0 to peak value front time. And then the another time is defined as time, because the front time is important, that how much steep the lightning is, how fast it comes. And the tail time is also important. This is called tail time. This is called tail time is also important, that how long it persists. Lower will be the tail time, it decays fastly. So this is the standard wave used to ideally simulate the lightning current or lightning voltage along any device. And the peak value of this impulse wave of this standard insulation of a particular equipment need to withstand. So as I have told you just now, just before this, that insulation level of any equipment must be greater than the residual voltage of the lightning arrestor. Then this is just the definition for that voltage characteristic or nature. So, and of course this BIL, that's why BIL of any equipment must be greater than the residual voltage of. So BIL of light of any insulator to be protected must be greater than the lightning residual voltage. And that's why how much will be the BIL rating for any insulator, any equipment, depends on the factors on which this residual voltage of a lightning arrestor depends. So the factors which cause the lightning arrested residual voltage higher will also cause the BIL rating of this. So I have think I have to leave by now. So we'll continue in the next class. And thank you for today. Okay. Hello.
Yes, sir.
हजुर है हजुर आजलाई यही छोडौँ मलाई हिँड्नुपर्ने भयो है अब टाइम पनि भयो अब यसलाई कन्टिन्यू गरौँला नेक्स्ट क्लासमा
हुन्छ सर।
ओके सर।
ओके हस् हस्